Okay, I'm going to try and do a complete the cosmological side of things, and also I'm going to throw in the weak force carrier. Anyway, I'm going to start with the sun, but before I do that, I just want to show that I've continued on constructing the relativistic slide rule, so that just with a quarter of this section, with a quarter of the section only, and only partially reconstructed it, so it goes out to infinity basically. But at this point, you can see that T is diverging, and now it's starting to converge. And at the point here, which I'm going to say is a black hole formation, there's no convergence or divergence, but inside there you start getting 1 over T diverging, and T continues converging. So you can see there's a point here where nothing's converging or diverging, but on either side you can see that here T is diverging, and here 1 over T is diverging, and the other one will be converging when the other one's diverging. See that? Okay, just leave that alone now, get rid of it. So let's start with the sun. Ta-da, there's the sun. And the sun will have a small b value, 0.0145692, and a radius of 695,700, 123. Okay. And what are we looking at? We're looking at the mass. That's correct. The gravity on the surface, it's strong. The 274 meters per second squared compared to the Earth, which is 9.8 meters per second squared. That's stronger than the Earth, obviously. Mean density of the sun, pressure. I won't bother with that because I'm going to use that later. Okay, so that's the sun. Maybe I'll also put the out to the distance that the Earth is rotating, and in that case I'd choose another 3 of those. 994. So that's a slower rotation out there, and the distance out to the Earth is 1.5 times 10 to the 11 meters. Okay, so now we're looking at the Earth's rotation, which is a long way out, and still the same mass, obviously, pulling on the Earth. The gravity out there is tiny. You can see it's sort of like the satellites going around the Earth. It's less. Not much time dilation. Velocity is obviously the main one I want to look at. What's the velocity? Yep, it's the velocity of the Earth going around the sun, about 30,000 meters per second. Takes a year to get round. Okay, so that's correct. Alright, so let's forget about the sun now. Go on to white dwarfs, which form after a supernova. So let me put in a white dwarf there. There's quite a range of B values for the white dwarf, and the same goes for the neutron star, but basically the a certain point the white dwarf will collapse into a neutron star. But anyway, let's start with a low B value, which is 0.01525, and with a radius of about the same as the Earth. So this is a white dwarf. It's going to have the mass of the Sun, but it's only got the radius of the Earth. So it's one solar mass. Gravity on the surface is going to be huge compared to this Earth or the Sun. 3 million meters per second squared, and so there's going to be quite a lot of time dilation on the surface. That's all I need to know, really. Pressure and density. Okay, what about it getting up towards a neutron star? Let's take that white dwarf up to 341 and drop its radius to about 17,600. Now we're looking at a solar mass of about 1.38, which is considered to be the point at which a white dwarf is going to collapse into a neutron star. Huge gravity, huge time dilation. You can see our density and pressure are starting to look like a neutron star. Okay, now let's just look at the neutron star. Here it is with its magnetic field. And so we're basically the same B value. And I'm just in a similar radius. This is considered to be the lowest solar mass, 1.4 solar masses. And it can get up to, well, I'm going to take it up to 0.6 because that's a nice round number. And I'm going to drop its radius down to that. So this is about the limit for a neutron star before it degenerates into a black hole. And so we're looking at about 2.43 solar masses. Well, that's probably considered more than it can handle. Gravity is huge. Okay, you see that's 0.36. What that means is let's subtract 1. It means that for, say, 1 year in outer space, only 0.64 of a year is going to pass on the surface of the neutron star. Okay, so it's going to lose about 0.36 units of time per unit of time in outer space, flat space-time. Escape velocity is going to have to is always over half the speed of light, so it's over 0.5. Density is huge, pressure is huge. I'm still a bit confused about all this. Apparently the a magnetar neutron star can have a magnetic field of about 11 Tesla, 10 to the 11 Tesla, but this should be Tesla, so that would only be about 8, 10 to the 8 Tesla there. So I don't know what's going on there. Okay, so that's a neutron star. Just notice that this relativistic slide rule is notice that what it's doing. It's actually it's like it's getting bigger, see? Whereas right in the beginning when we were talking about galaxies, it was way down here. We're talking about Earth and galaxies and stuff. It's very little gravity. But now we're starting to get some serious gravity. You can see that it's getting bigger and bigger and bigger like that. So anyway, what are we up to? We're up to the weak force carrier. So the weak force carrier has got a we're going to use the Weinberg angle, which is sine 30 roughly, which is a B of 0.5 if you know your trig. And I'm going to use I just didn't know what to do, so I thought, what happens if I put in the Planck length? So let's have a look. There we are with a proton, 2 up quarks and 1 down. This is usually the model. You can see the Weinberg angle. And you can see the beta decays, positrons and etc. Neutrinos, blah blah blah. What's that? Oh yeah, that's just my little diagram. You can see that you could get like 3 oscillators. Anyway, it's just a little, that would be a stable configuration. That's why I'm just speculating there. Okay, so what was my, you can see that's a bit high. It should be at the moment the latest value is 80.377, whereas I'm showing 93.118 MeV. So that's a bit big. Same with the Z boson. So that's the W boson. Okay, so I might have to drop my sine from 30, and in this case I find I have to drop it right down to 27.68, which is only about 0.464 B value. When I do that, well, it's spot on. The MeV is spot on, and of course it's huge. It's 80 times the mass of the proton, because the proton's only about 1,000, and this is 80,000. So how the hell does a mass of 80,000 come out of a mass of 1,000? Well, the explanation is the uncertainty principle, which means that the boson only survives for a tiny amount of time, and the less time it survives for, the more energy it can borrow. So that's the explanation it's given. It's supposed to be 10 to the negative 23, I think, but anyway, I get something almost as close to the Planck time, really short time. That's slightly out. It should be 90.2 EV. I mean GeV. Then comparing it to the other things, the Higgs expectation value, you can see it should be about 3.96 minus 3.49. Pretty close, but out. You can see that my SU2 gauge coupling is slightly out as well. You can see here what it should be. You can see here what mine is. You can see the U1 coupling constant should be about 3.86, mine's about 4.1, so again that's slightly out, which is of course all compounds and causes this to be slightly out. So yeah, I just can't get it to fit exactly if I want to use the latest measurement. Doesn't quite fit. It's pretty close though. Okay, so that'll do for the the weak force. Oh, maybe I'll just I'll explain this later actually. Okay, and then what do we get after that? Well, the only thing we're going to get after that is a black hole. And all black holes form, according to the slide rule, they all form at 0.7071, or to be exact, the square root of 0.5. And the radius doesn't matter. I think that the smallest radius for a stellar black hole is about the same as a neutron star actually. So, but anyway, so the notice that the kinetic energy required is precisely the amount of potential energy that a fermion particle would have, so it's right on the limit. And the escape velocity for a photon, which is a boson, would be 1, so it's right on the limit too. Let's take a what if the Earth was a black hole? Well, its radius should be 0.00887. That's the mass of the Earth. But imagine that all squished down, all your Teslas and your houses and everything just squished down to the size of a marble. That'll form a black hole. Gravity's huge. This just stays at 0.5 because B doesn't have an R in it, so so that's why I have to put gamma in. I didn't want to, but I have to. Otherwise I've got to put a radius of 0.0125, and that's not what's considered to be the radius. It's considered to be 0.00887, so I have to put gamma in. So we obviously, gamma would take it up to another reference frame, an outside reference frame. Maybe that's not the reference frame we're in the other reference frame. Yeah, not sure what's going on there. Universe is next. Now it's got a huge B value, isn't it? What is that? What does that mean? Does that mean it's inside a black hole? Does that mean we're inside a black hole? Well, let's put it in. Actually, I've already put it in here with the small b and r, so why not just use small b and r? No, actually, I'll put it in for the big. Let's compare densities. The density, if it was a black hole, what would be the density? Okay, so if it was a black hole, what would be the density? 9629739555961. Radius of the universe. And right, so that's the density of the universe at the moment. Now what if it was a black hole? Square root of 0.5. Same radius. A black hole with the radius of the universe. What would its density be? Better use a little less here because that's cool. Yeah, see, its density would be about the same, bit less. That's because T is the only thing that's changing, and doesn't have much effect on that value for the density. but I don't think it makes any difference whether we're inside a black hole or which is evaporating, which would be like a white hole or whatever. I don't know if it makes any difference anyway. Okay, that's the so anyway, that's the universe. Now looking at the CMB. Oh, did I actually have a picture for the universe? I did. There's my picture for the universe. Don't want you to miss out on any pictures. Okay, here's a picture of the CMB. And okay, let's put in its stats. Oops. Which are 1, 2, 3, 4, 5, 5, 8, 8. No, sorry. 8, 3, 3, 5, 8, 8, 2, 7, 1. And it's got a radius of 3.5757, 10 to the 21. You can see it's about 10 to the 24 all up. And it's the correct age. I've already been through this. That's the correct redshift, which is now the microwave background. Okay, I just wanted to go over this because notice that's the inverse of the fine structure constant. Now last time I didn't explain this on the diagram, so this time I'm going to let me just get rid of that. Put in a few lines. X is B and Y, and let me just put this in again. Now let me just look right up here. I'll just head in until I get to 100 and some. Oh, there we are. What's that? Ah, that's the value. So if the force was stronger by 137 back then at the time of the CMB, somehow, I don't know how, this could explain the alpha, fine structure constant. Okay, so that's how I was finding it. Now get rid of that and that, and in this case here I've made X B, which is L over T, so it's sort of like squished. This is the graph of mass, by the way. See how it's inversely related to gravity. Here it is at its maximum, and gravity is at its minimum at the same point. But you can graph it. I could make the x proper velocity, which would be 1 over t, and if I do that and just graph all the physical quantities, and I get this. And now I can just choose a b value. Let me choose 0.6. And you can see that when b is 0.6, then proper velocity is 0.75. And so you can see that the relativistic slide rule is just taking the derivative. It's just slicing through that all those functions and reading off the values. You see that? Time 1.3333, gamma here 1.25, and look at gamma. That's actually like special. That's actually the graph they use for special relativity, and they call that gamma, that function gamma. They actually call that time, and then proper velocity. And that's just x equals y. So they're converging slowly. So you don't need to distort space-time. You don't need hyperbolic geometry. Euclidean geometry is just fine, but you can still just carry on with your distortions and if you like. But anyway, at least with this one I can just read things off. I don't have to it's not just a pretty picture, you can get your ruler out and actually measure these lengths. Have I finished? Let's get rid of that. Shall I talk about aeropons? No, I won't bother yet. And we're going to get on to colours and diffraction, which is the Fresnel equations, and that requires me to use proper velocity 1/t. So it seems that light is I have to use phase velocity for light, 1/t, not the other one, L/t, which seems to apply to fermions. Yeah. Anyway, that's how the mass. That's how I have to do the mass, otherwise it doesn't work out. And I'll explain that later. Okay, that should be enough.